Well, whenever we have a solution, we have to consider how much of the solute you have per um, solution, right? So it's a concentration. So these are the different concentrations we have when we have solutions. We can talk about the mole fraction of a solution, the molarity of a solution, the molality of a solution, percent by mass, parts per million, and parts per billion. So all these different ways of expressing concentration of the solution. All right, mole fraction is, well, just like it says, right? It's going to be the fraction of the moles. So moles of the component you're interested in divided by total moles of material in the solution. So it could be moles of solute, it could be moles of solvent, right? Depends on what you're interested in, right? So it's moles of the component you're interested in divided by total moles. So you just add up the total moles and divide by the moles of the component you're interested in. So calculate the mole fraction of benzene and calculate the mole fraction of benzene and toluene in a mixture of 0.884 moles of benzene and 1.657 moles of toluene. So mole fraction of benzene would be moles of benzene divided by total moles. So moles of benzene plus moles of toluene. Mole fraction of toluene would be moles of toluene divided by total moles. Notice the mole fraction of both components has to add up to be 1, the total. Molarity we're already familiar with, right? Moles of solute per liter of solution. What is the molarity of a solution made up by dissolving 9.52 grams of sodium chloride in enough water to produce a 575 milliliter solution? So we just want to get the unit right. We want moles up in the numerator, liters of solution down in the denominator. So use the molar mass of sodium chloride to get to moles of sodium chloride. Divide by liters, right? Not milliliters, right? So for every 1,000 milliliters, we have a liter. So when I multiply across, grams cancel, milliliters cancel, and I'm left with the unit I want, the ratio of moles of solute per liter of solution. We've talked about this before, right? When we look at the formula and you're asked what's the concentration of the sodium ion in a solution where you've got 0.683 molar sodium sulfate, recognizing that what we have in solution, we have sodium sulfate is 2 moles of sodium ion for every mole of sodium sulfate. So it's going to be 2 times the molarity of the sodium sulfate solution. For every 1 mole of sodium sulfate, you've got 1 mole of sulfate. So the concentration of the sulfate would be the same as the concentration of the sodium sulfate. It's important later on we talk about what's called colligative properties, that we get total moles of particles in solution. So for every 1 mole of sodium sulfate, we look at that as 3 moles of particles, 2 moles of sodium ion, 2 moles of sulfate anion. Molality, I know, I didn't make it up. It's just the way it is. So there's molarity and then there's molality. Molarity was capital M. Molality is lowercase m, symbol for molality. So it's moles of solute per kilogram of solvent. So instead of liters of solution, it's kilograms of solvent. So determine the molality of a solution where we've got 0.345 moles of ethanol added to 168 grams of water. So just get the units right, right? Moles of ethanol divided by kilograms of water. So for every 1,000 grams, there's a kilogram. Now we have it in molality, moles of solute per kilogram of solvent. Percent by mass, mass the component you're interested in, divided by total mass of the solution. So it could be the percent by mass of the solvent or the solute. Determine the percent by mass of a 0.4 0.14 grams sugar cane and 50 grams of sugar syrup. So we got the mass of the solution, 50 grams, divided the mass of the component we're interested in, the sugar, times 100. Unitless, right? So whereas mole fraction was unitless, right? It's moles divided by moles, no unit. Molarity is moles per liter. Molality is moles per kilogram of solvent. Percent by mass is unitless. It's the percentage of the component you're interested in divided by the total mass. Parts per million, parts per billion. So this is when we have very small concentrations, right? So the mass of A in the solution divided by the total mass times 10 to the 6, and the mass of A in the solution divided by total mass times 10 to the 9. Diluting solutions. We ran into this earlier when we were talking about aqueous solutions with precipitation reactions. So you're taking a more concentrated solution and you're adding water to it to make a less concentrated one. So M1V1 is equal to M2V2. If I know what my initial concentration is and my initial volume, I can figure out what my final concentration is and my final volume. Liters times moles per liter gives you moles. So the moles of solute aren't changing, right? The moles are staying the same. What's happening is you're adding water. You're increasing the volume. So you're making the denominator bigger in the ratio, right, of moles per liter. So it's always the question when I'm diluting, if I have a concentrated solution like 12.5 molar acid and I want to make a 1 liter 1 molar solution, how much of the concentrated do I need to start with? So I plug into the equation every time, right? I know what my final concentration is. I want it to be 1 molar, and I want to make a 1 liter solution. So if I'm starting with 12.5 molar, 1 times 1 divided by 12.5 gives me a start of 80 milliliters. So I'd want to start with 80 milliliters of the concentrated and then add enough water to get up to 1,000 milliliters, and I'd have a 1 molar solution. Effects of temperature on solubility. All right, so is a solute more soluble or less soluble at a different temperature? When you're talking about gases in water, gases are always less soluble at higher temperatures. It has to do with breaking up that hydrogen bonding web, which traps the gas in the first place. So this is how a lot of fish die in fish tanks. As the temperature goes up in the water can't hold as much oxygen, and the fishy suffocates. As far as solids go, it varies with the substance. Some solutes are more soluble at high temperatures, some are less. Now, in general, most often the solubility of a solid solute, increases with increasing temperature. But that's not always the case. There are exceptions to this. All right, so this would be a problem, right? A saturated solution of potassium chlorate is formed with 100 grams of water. All right, so it's saturated. If you're cooling it from 90 degrees Celsius to 50, how many grams will drop out, right? So the solutions only can hold a certain amount of potassium chlorate at 90 degrees. So in this problem, they don't tell you how much. You'd need some tool to figure this out, and this is what a solubility curve is. It plots how soluble a particular solute is in 100 grams of water at a certain temperature. So we were talking about potassium chlorate. All right, so at 90 degrees Celsius, you've got a saturated solution at about, at 45 grams of solute. So anywhere along that line represents the saturation point of potassium chlorate. So you're able to get 45 grams dissolved. And as I cool it down, I go down to 50. Well, all of a sudden, you're not going to hold 45 grams anymore, right? At 50 degrees, we touch the line at about 17 grams? 18 grams, right? Depends on your eye, right? So the difference between 45 and 18 would be how much of the solute would drop out. So 27 grams of the potassium chlorate would drop out as you cooled it from 90 degrees to 50 degrees Celsius. All right, so there's some correlation between how what kind of enthalpy of solution you have and how soluble you're going to be at a different temperature. So in general, if you have an endothermic heat of solution, increasing the temperature on the solution will increase the solubility. So that's an endothermic heat of solution. If you've got an exothermic heat of solution, all right, heat released when the solute dissolves in the solvent in the water, you're going to get less soluble at high temperatures. So increasing the temperature will make it less soluble. So you'll go against the trend. The effects of pressure on the solubility of gases. Notice we say gases because when we talk about the solubilities of solids or liquids, it has no effect. Increasing the pressure on a solution of sodium chloride isn't going to make the sodium chloride more soluble. But it has a big effect on gases. So this is how soda works. You put the pressure on in terms of the carbon dioxide sitting over the water. You get more of the carbon dioxide to dissolve into the water, and that's what soda water is. Carbon dioxide gas dissolved in the water. So the way it works is you put pressure on, right? You have a certain equilibrium established, right? A certain pressure of the carbon dioxide gas sitting over the water. If I put pressure on it, I get more collisions with the surface, and I get more of the particles getting trapped. So I increase the solubility of the gas because there's more collisions with the surface going one direction, and you're not changing the surface area at all, so you're not changing the rate of escape. So increasing the rate of trapping by putting it under pressure and having no effect on the rate of escape. So you increase the concentration of the gas in the liquid. Establish a new equilibrium at a new pressure. So it's a direct relationship. The solubility of a gas is S. The pressure over the gas is P. So increase the pressure, increase the solubility. K is a constant that's going to depend on what kind of gas you're talking about, right? So oxygen is going to have a different solubility than nitrogen in water, which will have a different solubility than carbon dioxide in water. So each will have its own Henry's law constant that would equate pressure to solubility. Henry's law is only going to work as long as we're not having a chemical reaction occurring. Frankly, when you talk about making soda, this relationship falls apart in a way because the reaction with carbon dioxide and water, as we know, a non-metal oxide in water produces an acid. So you're lowering the solubility of the CO2 because some of it's reacting, making carbonic acid. That's what gives soda its twang. So what is the concentration of oxygen in water at 25 degrees Celsius if the pressure is 0.2 atmospheres? So that's just plugging in the numbers, right? They have to give you what the constant is in terms of moles per liter per atmosphere. Multiplied by atmospheres would give you moles per liter. So it's just plugging in the equation. And you get the equation on the AP exam, and I'll give you the equation on our test. So just have to know how and when to use it. Solubility of a gas increases with increasing pressure. Henry's law.